Dear students, continuing with the chapter Forced Vibration, this lecture is on the topic Analysis of Equations of Motion of Forced Vibration System with the Harmonic Force. I, Dr. Balraj Singh Brad, Yadavindra College of Engineering, Talwandi Sabo, India, am present. We are taking the case of forced vibration system with the harmonic force only, and the harmonic force is F is equal to F naught sine omega t. It is acting on a spring mass damper system, spring stiffness K, mass M, and damping coefficient C. So F is a dynamic force with and is vibrating with the amplitude F naught and frequency omega as shown by the figures. This plot. And we have already calculated that the solution of this problem means the equation of vibration of the mass is X is Xc plus Xp. Xc is complementary solution and Xp is particular solution. What we observe is for some initial period, this red plot shows the vibration profile, and slowly it becomes steady. Say up to this we have observed a transient vibration, and beyond this we observe steady vibrations with the constant amplitude, and of course the frequency is the same. Solution of forced vibration system with the damping we have already done. X is complementary solution plus particular solution. Complementary solution Xc we take for underdamped vibration system because in usual applications zeta is less than 1, and Xp is particular solution. It is of the type a constant amplitude A, sine of omega t. Omega is the frequency of forced vibration, minus phi. Phi is the angle by which the vibration of the mass lags behind the external excitation. Now A, we have already calculated amplitude of vibration to be Xs. Xs is zero frequency deflection. Means Xs is zero frequency deflection means if F naught is static, how much the mass will deflect. This is basically static deflections. That will be simply external excitation or force divided by the spring stiffness K. So we put value of Xs. So A is Xs by under root of 1 minus omega by omega n whole square and its whole square plus 2 zeta omega by omega n whole square. Zeta is the damping ratio. Omega by omega n is the frequency ratio. So A is known. We put A to find the particular solution, and the phase difference phi by which the system is lagging behind the external excitation is 2 zeta omega by omega n by 1 minus omega by omega n whole square. We calculate phi from this relation taking tan inverse of right side term. Now we had the particular solution, we put it and we get the complete solution. We have already done it. For initial period C constant and phi 1 can be determined from the initial conditions. This type, the transient vibration is there for a very small period of time and it ultimately vanishes. For most of the period, we have only vibration profile because of xp. So this is the steady state vibration which is there, and we make use of x is equal to this for most of the. Again, total response we have calculated. It is transient vibration plus steady vibration. Transient vibration is underdamped system vibration. This is steady state particular solution which is valid for most of the time. We overlap, we get the solution. So up to here we get transient vibrations, and beyond this we get steady vibrations. Now for practical purpose, our solution X is almost equal to xp for very large values of t. T is the time period. And as we discussed, solution xp is a sine omega t minus phi. Omega is the amplitude, we can calculate. Phi is the phase difference, we can calculate. Omega is the frequency of external excitation. So if we have a external excitation, say of amplitude f naught, and is vibrating, then its time period will be 2 pi by omega. Then we get a solution x solution which is almost equal to xp, like this. Only thing is we calculate this is the amplitude and this is the phase difference phi by which the system is lagging behind this, and time period for both the cases is same because now the system is under forced vibration and it is vibrating with the same frequency of excitation. We have drawn vector diagram. In the vector diagram we calculated that this is, let us use highlighter, this is the inertia force, amplitude is m omega square a. This is damping force with amplitude of c omega a. This is spring force with amplitude of ka. F naught is this is excitation force with amplitude f naught. Now at any time t, let the system complete turns omega t angle. So we make taking a reference, we take angle omega t, and external side excitation is f naught. So at omega t we draw f naught external excitation. Then spring force is lagging omega t by phi. We come back by phi and we draw the spring force with amplitude Ka. Then damping force is advancing the spring force by pi by 2. So it is advancing, means at 90 degree, and amplitude is c omega a. Then inertia force is advancing the spring force by pi, means it is opposing it. So it is in opposite direction, again 90 by 90 degree, and amplitude m omega square a. So resultant of all these is either 0, or we can say resultant of spring, damping and inertia force is equal to the external excitation. So this vector diagram we have used to derive, need not derive a amplitude of the vibration, forced vibration. It is xs. Xs is zero frequency deflection to under root of 1 minus omega by omega n square its whole square plus 2 zeta omega by omega n its whole square. Now, we will define a term magnification factor, or also known as amplitude ratio. It is a non-dimensional quantity and is defined as A by XS. From this relation, simply rearranging A by XS becomes 1 by under root of 1 minus omega by omega n square its whole square plus 1 minus omega by omega n square its whole square plus 2 zeta omega by omega n its whole square, where omega by omega n is the frequency ratio, XS is F naught by K, zero frequency deflection, and A is the amplitude. Now we know the amplitude ratio for our forced vibration system. Then we find maximum amplitude ratio or magnification factor A by XS. What is its maximum value? For maxima, we take derivative of amplitude ratio A by XS with respect to frequency ratio, which is omega frequency of external excitation to omega n natural frequency. And we put this derivative is equal to 0. We know the value of A by XS. We put it here. When we take the derivative, so this relation's derivative, it becomes minus, since in the denominator there is a square root term, so derivative becomes minus half. Now in the denominator, power is increased by 1 minus 1 by 2 plus 1, and it is there. Then we take derivative of this function, denominator function, and write in numerator. So we get, when we take derivative of this, we get 2 into 1 minus omega by omega n whole square into derivative of this dash term, it becomes minus 2 omega by omega n plus, we take derivative of this term, so it becomes 2 times 2 zeta omega by omega n into derivative of this 2 zeta. We put this is equal to 0. So 1 by minus 1 by 2 and denominator, when it goes to the other side, multiplies with 0, it becomes 0. So we take this term to the other side, we get this solution. In this solution, we will observe that this 2 and this 2 will cancel out. We can cancel out one more 2, anyone. Negative will cancel out with negative. 1 omega by omega n term cancels out with another omega by omega n term, and which on simplification results in 1 minus omega by omega n whole square is equal to 2 zeta square. When we rearrange, this gives the maximum or the frequency ratio, which is omega maximum to omega n, maximum frequency of excitation, at which we will get the maximum amplitude is under root 1 minus 2 zeta square. Next job is, we have to put this value into the A by XS relation to find out the maximum amplitude ratio value. So now We put omega by omega x, omega n, omega maximum by omega n, which is 1 minus 2 zeta square into a axis. So the terms here got changed. Omega by omega n, we put it to be omega maximum. Similarly, we put it here omega maximum to omega n. So we have got this relation. Now we have found omega maximum to omega n values for different zeta. When zeta is 0, no damping is there. Maximum amplitude is at 1, means at resonance we have maximum amplitude, and the relation gives that maximum amplitude ratio is infinity, means theoretically system should vibrate with infinity amplitude. Then we go on increasing zeta. Say zeta we increase to 0.2. Omega maximum to omega n value is 0.96. It means now we get maximum amplitude at omega less than omega n before the resonance, 0.96. When we increase zeta damping ratio to 0.25, it becomes 0.94, means we are getting earlier and earlier the amplitudes at 0.3, 0.91, 0.5, 0.707. But if zeta is 0.707 or onwards, we get no maxima. No maxima is there, and the amplitude is always less than 1. Amplitude value we can say A by xs is less than 1 for all, but for 0.707 it is equal to 1. Now what happens when zeta we are increasing from 0 to like this, with means we are introducing damping into the system, maximum amplitude is decreasing, say from 2.55 to 2.11 to 1.75 and 1.16, and this tells that maximum amplitude position we are arriving earlier at lower frequencies. As we are increasing damping, the maximum amplitude is shifting to the left. We are getting it at an earlier frequency of external excitation. Now we find at resonance omega is equal to omega n. If zeta is 0, then we know A by xs is approaches infinity. But for all other values of zeta, in this relation of A by xs, we put omega is equal to omega n. We put omega by omega n value 1 here and 1 here, and when we simplify this relation, this becomes A by xs at resonance is 1 by 2 zeta, means as zeta is increasing, the value of A by xs at omega is equal to omega n is continuously decreasing. We are getting lesser and lesser amplitude ratios. Then, knowing the equations and maximum amplitude ratio, defining frequency ratio, knowing the amplitude at the resonance, we draw characteristic curves for forced vibration system. We make two curves. First is frequency response curve, which is a curve between amplitude ratio or magnification factor versus frequency ratio. So this is the relation, this is the amplitude ratio, and this omega by omega n is the frequency ratio. We make plots for different values of zeta and different values of frequency ratio, and this is known as frequency response curve. Second characteristic curve which we make is phase frequency response curve. It is the curve between phase difference and the frequency ratio. As zeta and omega by omega n are varying, phase difference phi varies, and we will be plotting. Frequency response curve, as we have discussed, is the curve between amplitude ratio A by XS, amplitude of vibration to the static deflection, versus frequency ratio omega of external excitation to the natural frequency of the system. What we observe is for all values of omega is 0 means external excitation frequency is 0. It is external force is steady. We know A by axis is 1 means amplitude is equal to static deflection for all values of zeta, and we get this point for all values of zeta. Then when omega by omega n is 1 means at resonance, for zero damping, we get amplitude ratio of infinity, which is as per the definition of resonance. And when zeta is 0, this is the plot. Then for omega by omega n, one value, omega is equal to omega n at resonance, what we get is infinity amplitude for zero damping system. But as we increase the damping, introduce the damping, we know the relation we have derived, amplitude ratio becomes 1 upon 2 zeta. So when zeta is increasing, amplitude ratio is decreasing. For zeta 0.25, zeta 0.5, zeta 1, zeta 2, zeta 4. So we have different plots. This plot is zeta 0.25, this is zeta 0.5, this is for zeta 1, this is for zeta 2, and this is for zeta value equal to 4. Next, not only at resonance, the amplitude ratio A by XS reduces for all the cases. Whenever we are introducing the damping into the system, amplitude ratio is decreasing for all frequency ratios. Say, when omega is quite less than omega n, this frequency ratio, say this is amplitude ratio at that frequency ratio for zeta 0, for 0.25 with slight introduction of damping, it decreases, then 0.5, then 1, then 2, then 4. Even for higher frequency ratios, omegas greater than natural frequency, it keeps on decreasing with the increase in damping. Now let us focus on maximum amplitude ratio. What we observe is When omega was equal to omega n and zeta was 0, maximum amplitude was infinity. But when we introduce zeta into the system, maximum amplitude ratio for 0.25 is this much. So this, with increase in 0.5, it decreases like this and like this. It keeps on decreasing, and more the maximum amplitude we are getting at lower external excitation frequencies from here to here. As we discussed in the table in the previous slides, it is shifting to the left. But when zeta value is greater than 0.707, A by R is greater than or equal to 0.707, A by XS is less than or equal to 1. When zeta is 0.707, A by XS is 1, maximum value is 1, then it decreases. Means for all higher zetas, for all higher values of zeta, the amplitude ratio is less than 1. When higher damping is there, amplitude ratio will not increase. One more observation is there. When frequency ratio is large, say 3, means external excitation frequency is 3 times the natural frequency of the spring mass system, then the amplitude ratio is quite less. Next is phase frequency response curve. We make a plot between phase angle phi and frequency ratio omega by omega n. Maximum phase difference we get is 180 degree, lowest is 0 degree, and we similarly range for frequency ratio is 0 to 3. What we observe is this is the plot for zeta 0, red color. What it shows is at 0 damping, phase difference is either, let us first discuss 0. At zeta 0, damping is not there. Phase difference is either 0 or 180 degree. So it is like this, either 0 or 180 degree. Next, we have made different plots. Say this is for damping ratio 0.05. This light green is for 0.3. This dark green is for 0.5. Cyan color is for 1. And this dark blue color is for 2. What we observe is for all values of zeta at resonance, means omega is equal to omega n, phase difference is 90 degree. You take any curve when omega by omega n is 1, for all, whether this curve, this curve, this curve, or this curve, phase difference is 90 degree. And more, for higher frequencies, as we are increasing the zeta, phi is decreasing like this. We have observed zeta is increasing, phi is decreasing. And for low values of zeta, we get higher phase difference. For lower values of zeta, we get higher phase difference when we are on the right side of the plot, means omega is greater than omega n. So this is usually the case. We will be getting the frequency phase difference from 90 to 180 degree for low dampings, higher values, higher dampings, less values. At resonance, it is 90 degree, but for low external excitation frequencies, the case is different. Phase difference is more for more damping. As damping ratio is decreasing, phase difference is decreasing. Trend is reverse. We have the plots like this for higher, when decreasing like this, then like this, then like this. Next is variation of frequency ratio. What is the effect of frequency ratio on the vector diagram omega by omega n? We will discuss. We can take three cases. Case 1, when external excitation frequency is very less than natural frequency. System is subjected to a forced vibration of very low frequency. Case 2, omega is equal to omega n means at resonance. External excitation frequency is equal to the natural frequency of the system. Case 3, omega by omega n value is greater than 1. Omega is much greater than natural frequencies, means at very high frequencies of the forced vibration. For case 1, when external excitation frequency omega is very less than natural frequency of the system, means at very low frequencies of external excitation, we get F external excitation at an angle omega t is here at any period time period t, we will get omega t. So F naught is there drawn at omega t from the reference line. Then spring force lags behind the external excitation by phi, and for very small values of omega, c omega a amplitude is less and m omega square a amplitude is further less. Of course, the angle between spring and damping force remains 90 degree, between the damping and inertia force remains 90 degree, and we get a vector diagram like this. As omega is decreasing, phi keeps on decreasing and it approaches to 0 for very low frequencies of external excitation. Means system is vibrating almost in synchronization with the frequency of external vibration. And when omega is very less, we can find out that amplitude F naught is almost equal to Ka. F naught is Ka. So A is equal to F naught by K, which is X static. So it means A by static deflection approaches a value of 1 for omega very less great than omega n, means near to 0, near to static conditions, as we have discussed in the characteristic of frequency response curve. For case 2, at resonance when omega is equal to omega n, C omega A has some value, reasonable value. M omega square value is large now. External excitation is F naught. and at resonance they make a rectangle like this. What we observe is value of external excitation amplitude is equal to C omega. F naught is C omega A, or simply amplitude of the vibration A is equal to F naught by C omega. C omega. We can determine from this relation. More, amplitude of spring force Ka is equal to m omega square A. Of course, these two forces oppose each other, but their amplitudes will have the same value at the resonance. For case 3, when omega is very much higher than omega n, means at very high frequencies of force vibration, we have spring force, we have damping force, we have inertia force. Now, the of course spring damping force is at 90 degree to spring force, inertia force is at 90 degree, omega t is any journal angle at time t with reference we have taken. Now phi is the phase difference between by which Ka lags behind the external excitation F, or its amplitude is F naught. What we observe is when omega is large, omega square will be quite large. Means the inertia force will have very large magnitudes, resulting in phi approaching 180 degree, and we can say amplitude of inertia force is almost equal to F naught plus Ka, forgetting about their directions, only amplitudes. So phi approaches 180 degree, and inertia force is quite large because it has a term m omega square A. Omega is quite large. With this, the lecture on analysis of equations of vibration of forced vibration systems with harmonic analysis is complete. Thanks, my dear students.